So this video covers section 10.4, which is using inscribed angles and polygons. This is where we now go away from central angles, and we have a new type of angle called the inscribed angle. So for an inscribed angle, it is an angle whose vertex is on a circle, and whose sides contain chords of the circle. So we've had a central angle, we talked about a couple sections ago, and that's where vertex is based in the center. And inscribed is going to be on the circle. So we have a vertex, some point on the circle. Let's call it our inscribed angle. And then it says the sides go out and they contain some of the circle. Well, that part of the circle, that arc, is what we call the intercepted arc. And that's that distance right here. That's that arc of the circle. So we have an angle matches up with some arc. We call that the intercepted arc. Okay, so we're going to have, where we did the same thing with a central angle looking at values, we're going to do the same thing with an inscribed angle. So our first theorem tells us that. Theorem 10.7 tells us the measure of an inscribed angle is 1/2 the measure of its intercepted arc. So I look at angle ADB here. ADB is right there. That is equal to 1/2 the measure of arc AB, which is out here. Now, that fits to what the theorem says. Let's shorten it up and say the inscribed angle equals 1/2 the arc. That's our general rule for the inscribed angles. Now, if you don't like that 1/2, you want to move it over, you could say the arc is 2 times the inscribed angle. That would also work. So arc is twice the angle, or the angle is half the arc. That's the relationship we have between them. So let's just start off with some basic examples. And we can kind of keep going, make it more complicated if we need to. So 50 degrees is my angle. So the measure of the angle equals 50 degrees. Then the arc is, well, twice that, 100 degrees. Okay, we do it again. This time, let's say we have an arc that is 150. So I need the arc to go to the angle. Well, if the arc equals 150 degrees, then the measure of the angle would be half of that, would be 75. Now, it's half of that. And let's take a second here and think about this problem. Maybe it's something where we remember it's 1/2, it's double, we have that relationship there, but we mix it up. Okay, if we think just kind of common sense, not so much sticking with the rule, but kind of, does this answer make sense? If I had this arc at 150, actually this doesn't even represent it very well. This would probably be this more closer to 100 degrees, if what it represents in the circle. But let's say I have an arc that's 150. If that arc and that angle have a relationship between them, and I can't remember, if I go from an arc that takes up a lot of the circle to an angle that's going to be fairly smaller, I'm making it smaller. I'm going to divide by 2. Whereas if I go from an angle that's pretty small to an arc that looks like it takes up more of the circle, I'm going to double it. What I'm getting at here is, don't put this, if you're given this is 150, and then write the angle as 300. That doesn't make sense, because our angles will always have to be less than 180. They're always smaller than 180 that we look at. The arc, well, it could theoretically be a very large arc. I mean, it could be close to 360 degrees. But the angle is not going to be more than 180. So the angle is always smaller. So when you go to the angle, you make it smaller. If you go to the angle to the arc, you're going to make it bigger, because the arc can always be bigger. So just kind of keep that thought in mind. So just if you get an answer, just quick check, does this make sense? You can look at it that way. Okay, the last one, we're just getting used to the process here. We got 4x and x plus 7. It uses the same idea, but now we just have to get that set up. Well, I want to half the arc, so I'm going to do 1/2 of 4x equals x plus 7. 2x equals x plus 7, and x equals 7. So if we went back and checked, that means the arc would be 14, and if the arc's 14, then the angle is 14, and the arc would be 28. Okay, before we get to some practice problems, let's look at another theorem, and we'll come back to it, of course, but this has to do with inscribed angles. This says if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So, looking at this example, if I look at just angle D, and let's kind of cover up that other one. Just looking at angle D, that goes to arc AB. And that angle would be half the arc, like we just talked about. Then I come up here and I look at angle C. Let's move my hand here. If I look at angle C, that matches up to arc AB. It's half the arc. Notice how both of those angles go to the same arc. Well, if I knew this arc and I wanted to find each angle, I would divide it by 2. Well, I'm going to divide the same number by 2, so that means I'm going to get the same angle. Because these angles go to the same arc, they're going to be congruent. Okay, so let's say I have an arc here from point to point, and I draw an inscribed angle, and I draw another inscribed angle, and I draw another inscribed angle, and another one, and another one. In between any two, I could draw another one, and another one, and another one, and another one. And all of those angles would go to the same arc. So, if this arc was 90 degrees, every one of those angles, as long as they go to that arc, would be half of that, and they'd be 45 degrees. And if the angles are the same, then they're congruent. That way, anytime they go to the same arc, they're going to be the same angle. Now, this is a statement that exists. We're going to see in an example where it does make things a little easier, and it's kind of a shortcut to when we solve them, but maybe we didn't remember this. Okay, let's say I'm looking for I have this angle, and I want that one. Well, hopefully you look at this angle and you say, I can find that arc, and then you see that arc, you say, I can find that angle, and it's 2 steps to get there, or in this case, you just recognize they go to the same arc. They're going to be the same. So, let's try some out here. So find the measure of the red arc and angle. I don't know if you can see the color on the video, but we'll just go through them together. First one we're looking for is right here. So the angle goes to the arc. The arc is 90. The angle is smaller, so it's 45. It is half of 90. Let's kind of go a little bit further and kind of review some other things as we go through it. If that's 45, all right, let's think of arc GF. Arc GF would also be 90 because this arc HF is 90. It's the diameter from G to H, so also 90, and this would be 180 if we needed that. Okay, number 2, I have the angle. I need the arc. So I'm going to make it bigger. I'm going to double that, so that would be 76. Would be arc TV because I doubled it. Could I find anything else? Let's be careful on this one. This is not a diameter. We do not know if that goes to the center, UV. So, can't really find anything else. We found 76. That's really all I was asking for, so we're good there. Now, number 3, we have angle Y is 72. This is the one where we have 2 angles that go to the same arc. So, if we look at it the long way, angle Y goes to what should be ZW there. So, I know that this arc is 144. Now, when I have this arc and I want to find angle X, I can take half of that, and it is 72. The angles go to the same arc, therefore they're the same. We know the measure of angle Y equals the measure of angle X. That's why they're both 72. Okay, now let's add a little bit more. Let's not just look at angles now, let's look at inscribed polygons. So an inscribed polygon we're going to define as a polygon where all the vertices lie on a circle. And then the circle that contains those vertices is the circumscribed circle. So we really have 2 types we're going to look at. We're going to have an inscribed quadrilateral and an inscribed triangle. And we could really look at any type of polygon, hexagon, octagon, any more and more sides, but we're really going to focus on these 2 in particular. The first one we're looking at is a triangle. So this theorem really has two parts. It's kind of the original statement, and we look at a converse of it. And it says, if a right triangle is inscribed in a circle, then the hypotenuse is the diameter of the circle. So, there's my triangle. And I'm saying, if it's a right triangle, where B is a right angle, then the hypotenuse would have to cut through the diameter of the circle. Okay, we can see that. Next one, if one side of an inscribed triangle is the diameter, okay, goes through the center, then the triangle is a right triangle, and the angle opposite the diameter is a right angle. Okay, that works too. If that cuts through it, we know B is going to be a right angle. Now, we fit it to the diagram. We say if measure of angle B is 90 degrees, if and only if AC is the diameter. Again, we're seeing right angle. This is the diameter, or the hypotenuse. So, AC is the diameter, and the measure of angle B is 90 degrees. So, let's look at an example. Let's label here. Let's say all they gave me was that. You have a circle, there's an inscribed triangle, AC is the diameter, and you have that angle C is 25. Let's look for angle A. Let's say we want to fill it in. So, I know since this is the diameter, it is a right triangle. We have a right angle here, which means this is 90. If that's 25 and that's 90, I can find angle A because it's the complement to 25, which would be 65. So that right triangle is going to fit in. 65 is going to be the measure of angle A. I now have all my values. Well, let's go a step further. We know that's inscribed angles here. That's 65 and 25. Even the B. Well, B is an inscribed to arc AC, this arc. So if that's 90 degrees, that means this one is 180. How about 65? Let's see at A. Well, if we're going from angle to arc, we want to make it bigger because the arc is going to have bigger numbers. So we double that. That's going to be 130 from C to B. And then, let's write this one too, arc AC. Okay, and now 25. That's going to go out and make the arc AB have a measure of 50. So even by just having that 25, I could fill in additional values. And maybe a higher end problem will have that. They just give you that triangle and they want arc CB. Well, we know it's a right triangle. You can find that 65. Inscribed angle goes out to 130. Not difficult calculations by any means as we go, but it's using these different properties and understanding how they all fit together. Okay, next let's go to our quadrilateral. So this one's different than the triangle. This says a quadrilateral can be inscribed if and only if its opposite angles are supplementary. So my opposite angles are E and G. So add them together, I get 180. And then F and D. Add those together and get 180. Now, I know we just finished our chapter on quadrilaterals, so it's really tempting to say, oh, well, E and G must be equal because they're opposite. Maybe they're parallelograms, or E and D have some relationship because they're next to each other. No, doesn't work here. This is inscribed in a circle. This has its own set of rules, and we can't go applying other things. Now, if they told us it was a certain type of quadrilateral, okay, we could use those properties, but right now, all we know is it has four sides and it's inscribed in a circle. So we have to follow the rule we're given, and that's they are supplementary. Now, maybe it helps us here, things to be aware of. All angles also add to 360 because it is a quadrilateral. And another thing to be aware of is they're all inscribed angles. And maybe we could use that to find an arc. So if I had angle G here, I know that matches up to arc FD. Maybe on a more difficult problem, that's something that occurs. So those are just things to be aware of, but what it's really, the main focus here is the opposite angles are supplementary. So let's use that. I look at example A. Well, 80 plus X equals 180. 75 plus Y equals 180. So I solve for X, I get 100. I solve for y, I get 105. There's my values. I go to b. Okay, I have a little more a's and b's here. Now, this even guides us in this problem, because I'm not going to say something with a plus something with b equals 180. I'm going to typically match up the variables. So it is 2a plus 2a equals 180. 4a equals 180, so a is 45. Then 4b plus 2b equals 180. 6b equals 180, so b is 30. I can plug those in. A is 45, so those are each 90. B is 30, so we get 60 and 120. And if we look at that one, this one actually appears to be a kite, because we have one set of opposite angles the same, and that would kind of fit in that description that we have for a kite. All right, I think we got one more set of examples here using our inscribed quadrilateral. So we can do those together. First one, we're going to say x plus 82 equals 180. I subtract 82 from 180, and I get that x is 98. And then 68 plus y equals 180. Subtract 68 from 180, and I get that it is 112. Second one, c plus 2c minus 8 equals 180. Gives us 3c minus 8 equals 180. 3c equals, oops, didn't copy the problem down right, it should be minus 6. 3c equals 186, so c becomes 62. And then to solve for x, 10x plus 8x equals 180. 18x equals 180, and x would be 10. So as you go through and do your problems, keep in mind it really comes back to inscribed angles here. They're half the measure of the arc. Arcs can go up to 360, angles can only go up to 180, so you're going to have to make them smaller when you go to angles, bigger when you go to arcs. That helps you remember your 1/2 measurement. And then inscribed quadrilaterals, opposite angles are supplementary, and inscribed triangles, a right triangle will go through diameter. So keep those in mind, look at your notes as you do the problems, and good luck.